Okay guys, the next chapter is about electrochemical cells, and there's two types of electrochemical cells. The first one we're going to talk about in the first lesson is Voltaic cells, and the other one we're going to talk about is electrolytic cells. But Voltaic cells are always spontaneous chemical reactions. We use these most of the time. If I were to say, when have you guys ever experienced a voltaic cell in your life? This is what you call a battery. So most batteries are a sequence of voltaic cells that all spontaneously generate electricity for us to use. Okay, so this is really how a battery works. Okay, so the thing you got to remember is that you have to have two separate compartments. And every battery you've ever seen has the negative end and the positive end of it. Okay, I'm going to use red and black for that because on your car battery, the red terminal is always the positive end and the black terminal is always the negative end. Okay, so I'm going to make sure we have those labeled for voltaic cells. And that's really important because if you remember way back when we did ionic compounds, the negatively charged ions are called anions. So this wire is called the anode. Okay? The negative end of the battery is always called the anode, and the positive end is called the cathode. Okay? And you'll understand why I've got this ABC here in a minute. Okay? But basically what happens is you have some chemicals in the anode that will perform chemistry, and you have some chemicals at the cathode that will perform chemistry, and in order to do that, electrons have to go through this wire and travel from the anode to the cathode. So I'm going to put the electrons in green, and they flow from the anode to the cathode. Okay? This B in the middle is really important. Okay? It's called the salt bridge. Okay? As the electrons move one direction, you usually have to move ions across the salt bridge in order to keep the chemistry going. And so if you don't have them connected using a salt bridge, the whole thing won't work. So the way I learned it was that voltaic cells are just your ABCs. Okay? You've got the anode, the bridge, and the cathode. And then what I did is I drew a little knob out there to make it look like a battery. Because this is what we would assume. This is the negative end, this is the positive end, and this is the basic outline of what a voltaic cell is and what it does. Okay, now part of that, and the reason why I learned it like this, my teachers taught me that, and if you remember from last unit, we have oxidation, and we have reduction half reactions. Okay, so what's happening is one of those two half reactions is taking place at the anode, and the other one has to take place at the cathode. And combined, it is one electrochemical reaction, but because we're making the electrons pass through a wire, we can now use this movement of electrons to generate a voltage for us, and that's how we can use these batteries. So the same reason why it's ABC over here, O comes before R in the alphabet, and so oxidation comes first, which means it happens at the anode, and the reduction always happens at the cathode. It's really easy. Questions in the book will be like, which of the following reactions happens at the anode? You have to select one that's an oxidation. Okay? So you've got to tie all of these vocabulary words, anode, bridge, cathode, oxidation, reduction, to this picture. So make sure you understand, if you draw it from scratch, always put the anode on the left, the cathode on the right, That way the electrons go clockwise. The salt bridge always goes in the middle. Okay, so an example of this would be, we could have zinc becoming zinc plus 2 at the anode. So that would be our oxidation. And on the other side, we could have copper that was dissolved in the water on the right-hand side, reduce back to pure copper. Well, in order to do that, this zinc would have to generate 2 electrons, and those 2 electrons would travel through the wire up and around, and as they came down into the solution on the right-hand side, every copper in this solution on the right would now gain those 2 electrons to become neutral copper atoms. Okay? So this is your oxidation half, that's your reduction half. The full chemical reaction would be zinc plus copper 2 makes zinc plus copper, and this would be our full electrochemical reaction. Okay? This is how we learned how to do it last chapter. Okay? But that is a lot of writing to try to explain what's happening. So the way we do it with batteries, there's a shortcut. Okay? And so what happens is, you put a line here, and I'm going to put an A above it. It'll make sense in a second. Put 2 lines in the middle, that's a B. And then I'm going to put that line there, and it's a C. Okay? So if you look at the picture up here, if I were to move these 2 beakers close, really, really close together, the right wall of this beaker and the left wall of that beaker would look like that. And then the outside wall of this would go there, the outside wall of that would be there. So the way we denote these is at the anode, we have zinc becoming zinc plus 2. And then over here in this other side, at the cathode, we have the copper plus 2 becoming copper. And so this is the shortcut that we use if we don't want to have to draw this whole setup. But you got to understand how the setup works. All of this information is contained in this shortcut. So you just have to make sure that this is an oxidation, and you have to make sure this is a reduction, and the bridge is always in the middle. So hopefully that, on top of reading what you read in the book about it, and the book has way better drawings than I can do, hopefully that helps you understand at least how voltaic cells are put together. Alright, so we've already drawn the picture for how to draw a voltaic cell and how to set it up. So now we're going to discuss how to know A, which way will make it spontaneous, and B, what would be the voltage of a cell. And so just knowing that it'll generate electricity is useful, but we need to know exactly how much. Okay, so in your book on page 667, there's a gigantic table that has the reduction potential for almost everything that we would ever want to look up for a regular chemistry class. Okay, some of you will notice that that list looks very, very similar in order to the activity series that we learned way back when on how to do signal replacement reactions. And if you remember, signal replacement reactions are all electrochemical reactions. So it is the same table. It's just rather than needing to know who's more reactive than the other one, we need to now know how much more reactive they are. Okay? So the first thing I want you to make sure you know is that what a reduction potential is. Okay? A reduction potential is the voltage required to reduce whatever species you're talking about. Okay? Now remember, when we're doing these voltaic cells, one of them is going to be oxidized and one of them is going to be reduced. And so what gets confusing is you will think you have to flip the math depending on what you're doing, but the math formula takes care of that for you. Okay? So I want you to look at the reduction potentials for the two chemicals we just did when we drew the voltaic cell. Okay? The reduction potential for the zinc to reduce requires a negative 0.76 volts. Okay? That is bad for you. That means you have to give it electricity in order to make it reduce. Okay? The copper's reduction potential is positive 0.34. That is good for you. That means that if you let copper reduce, you get 0.34 volts out of it. Okay? So the thing you got to remember is the substance or the species with the best reduction potential will reduce. Okay, so between these two, the copper has the best reduction potential. So it is going to be the one that goes from +2 to neutral. So we've got to put it at the cathode. Okay, and the zinc will be the one that will oxidize. So we need to put Zn and Zn +2. So we now have mathematically explained why we should, if we want this to be spontaneous, put the copper at the cathode, the zinc at the anode. Okay, and again, I'm going to draw this to try to get your guys' brains to tie something that you already knew. Okay, this would make a single-cell battery, which we call a voltaic cell. Okay, now for the math. Okay, so we want to now know the voltage that this cell will give us. Okay? And the formula is very similar to one that we've been using all year long. It's going to be the standard reduction potential of the reduction minus the standard for the oxidation. Okay? Now, if you've been drawing the batteries the way I've been teaching you to, it should match to what our heat of a reaction was. It was always the products, or the right-hand side, minus the left-hand side. And the name of these reactions are called redox reactions. So if you remember that these are called redox, the math formula is always redox. And the important symbol in here is the minus sign. Okay? The minus sign is why you do not have to flip the 0.76 for the zinc. If the zinc hates reducing, then it likes oxidizing, which is why we just subtract here. So it takes care of it for you. So for this voltaic cell, we get 0.34 volts for letting the copper reduce, and we get 0.76 volts by letting the zinc oxidize. When you subtract a negative, you see how this flips that sign for you, so you don't have to think about it. You just need to plug the two numbers from the table in. Okay? And so for this answer, our cell would generate 1.10 volts. And remember, notice how it's positive. Okay? If you ever get a negative answer here, you have just created a non-spontaneous cell, which we will talk about in the next unit. Okay? But for all voltaic cells, this answer must be a positive number. So what that means is if we have one of these batteries made, one of these cells, it will give us 1.10 volts of electricity. Now most of you, if you've got a device nowadays other than your cell phone, which has a super fancy battery in it, most calculators require more than one battery to operate the system. So what they do is they take, let's say we were using zinc copper batteries, this would give you 1.1 volts. We would then sequence the other one in reverse order so that it's in series. And those of you in physics, if it's in series, you will add the voltages. Okay, and we put another one in there, we get 1.1 volts. So if you have a calculator that requires 2 volts to operate, if you're using this battery, it's going to require that you put 2 batteries in alternating direction so that you can put them in series, and you now have inserted what is equivalent to a 2.2 volt battery. Okay? This is the physics side of things, and those of you that are in physics currently or engineering, right, you guys have had to do these diagrams where you've got your, and I can never remember the order of it. Here's your battery, I think it goes the other way. And you've got a resistor, and you got another resistor. Okay? This right here is your voltage. Okay? That is your cell, your voltaic cell that you're using to drive this circuit. And then you have to learn, V equals IR, and all of your other electrical formulas that you use. But this is how you build a battery that you would then plug into a circuit. Okay? Alright guys, and now we're going to do an example problem from the book. So if you look on page 672, question number 4, okay, it gives us this electrochemical cell. And it wants us to determine whether this will be spontaneous or not. And so this ties into our last chapter, because what we do is we identify that our tin is going from 0 up to 2, so it's being oxidized. And our copper is going from 1 down to 0, so it's being reduced. That's the first thing. The way I always did it was I rewrote this so that it made more sense to me in the electrochemical cell form. So I went SN to SN plus 2. Then I draw the salt bridge, and then I do Cu plus to Cu. Okay? Now, once I've got it like this, I can now check my chart and write down my reduction potentials. So if you go to the table on 667 again, the giant table, okay, the copper plus 1 is the 7th one from the top on the right hand column, which is 0.521. And the tin is located, plus 410, the 4th one from the bottom on the left hand side. So this is negative 0.1375. So I'm going to go negative 0.138. Okay. So make sure you look up those numbers and make sure I've got the right numbers there. And now you just plug in those numbers into our equation. So our cell potential is going to be the potential of the reduction minus the potential of the oxidation, okay, which is 0.521 minus negative 0.138. So the cell potential is going to be 9 positive 0.659. And remember, if this is a positive reduction potential, then this will be a voltaic cell. It is spontaneous. It generates 0.659 volts of cell potential. Okay? Every problem like this, you just run the same math equation. If you get a negative answer, it's non-spontaneous. If you get a positive answer, it is spontaneous.